Welcome to the Thursday seminars. It's my distinct pleasure to introduce Dr. Reid Corbett. Dr. Corbett is a professor and senior scientist in the Department of Geological Sciences in East Carolina University. And according to the website, tomorrow starts here, and with so many hurricanes, maybe that is true. Reid is also the program head at the Coastal Processes Institute at UNC Coastal Studies, and that's a partnership between several of the universities that are listed here, and pretty nice building, and is meant to bring a lot of people with different interests together and try to focus on research and education. So Reid is a little bit used to being in remote places like some of us are. Reid is also the chair of the ECU Coastal Studies Strategic Planning Committee, and that committee is tasked with coming up with a strategic plan that maps out the next decade for ECU involvement in coastal research, instruction, and outreach. More specifically, Reid is interested in sedimentary and geological processes in the coastal environment, and he uses naturally occurring radioisotopes to trace sedimentary and biological processes and to quantify sedimentary rates. Reid and I crossed paths at Florida State University, so when yesterday he sent me this message telling me things aren't good. We had to land in Greensboro, not Charlotte, as scheduled. Apparently, a landing plane ahead of us hit a deer. So when he told me that, I immediately thought, yeah, right, you got to try harder, come up with a better excuse, Reid. And so I went on and actually checked, and indeed, there was a deer that had an encounter, unfortunate encounter with a plane when they were taking off and or landing in Charlotte. And
it didn't end well for either.
Right. And the plane was leaking fuel and had to return and make an emergency landing, so I was certain that this was indeed true and not, like some of you thought, fake news. So Reid has been a lead PI on more than 20 grants and contracts over the past few years, and he has been on chief scientist or co-chief scientist on 15 of the 25 cruises that he has done worldwide. And I believe today Reid is going to tell us a little bit more about his research and program. Without further ado.
Great. Thank you, sir. All right. First, I'd like to thank you guys for inviting me to provide a seminar. I'm happy to talk about the work that I'm doing and sort of my research interests. I was supposed to be here in the fall, and so when this plane episode occurred, I was like, maybe I should turn around. This is kind of scary. Anyway, I'm happy to be here, and I'm happy you guys are here to listen. As most presentations go, especially coming from, I have a hard time thinking that I'm a senior scientist, but I do have senior moments. But what I'm going to present to you is a product of not just me, clearly, but many of the graduate students that I've worked with and many of my colleagues at ECU and well beyond that. And so I want to certainly acknowledge them and thank all those that have provided the support to do the research that I'll talk about today. And so Behzad did mention that I'm currently at East Carolina University, and East Carolina is here sort of in the floodplain of North Carolina. And I've been at ECU for about almost 18 years now, and 5 years ago I moved out to the coast, to the Outer Banks, and currently work at the Coastal Studies Institute, which is an interinstitutional institute within the UNC system. And so I live sort of right out here on the barrier island. Occasionally do have to commute back to campus. And so, the interesting interaction between a marine center, sort of a remote marine center, and its home institution is challenging, but also exciting and provides opportunities for a lot of the students, both graduate and undergraduate, that I'm really not going to talk about today, but have been involved with over the last 5 years since I've moved out there. What I want to talk about is sort of my research interest, and as you'll see, I want to sort of touch on all of these throughout this talk. My research interests are sort of threefold. They focus on sedimentary processes, a lot of it using natural radioactivity to understand sort of timing, provenance of sediments. the deposition, long-term accumulation, as well as disturbance of those sediments. I got started sort of in the sciences with my PhD focused on coastal hydrogeology, looking at groundwater discharge into the coast, and have gotten back into that in the recent years, and I'll talk a little bit about one of the projects on that. And clearly, it's hard not to live on the coast as a scientist and not focus on coastal change. And within North Carolina, I've become more involved in sort of management aspects of the coast, working with our Division of Coastal Management and looking at things like shoreline change, both on the ocean side, but in our large estuarine system, and over the last several years focused on sea level rise, which I talked to some of the graduate students about earlier. My interests are fairly broad, and the techniques that I use, I think, are also fairly broad, and they're broad sort of in what I do, but also in the timescales that I look at. And so I do use a lot of geochemical techniques. I use geophysical techniques, from ground penetrating radar to seismic surveys, bathymetric surveys, things of that nature. We do collect a lot of cores and analyze many different isotopes depending on the scale from those cores. And over the last probably decade, I've done a lot more work using more tripods than moorings, sort of shallow tripods with things like current meters, ADVs, and other sensors to try and get thinking about timescales, looking at things from minutes to months to decades. And much of that sort of lays on the use of radioactivity. And I don't want to get into great detail, but what you'll see is sort of the thread through this talk is the idea of using different radionuclides as tracers for process. And all of these different radionuclides have a different chemical sort of history, if you will. They have different chemical properties. They have different reactivities in fresh versus salt water. And so you can use these as great tools for processes within the marine and freshwater environments over varying timescales, using the fact that they have a half-life, and those half-life varies from seconds to millennia. And so you can use that as wonderful tools within the marine system. I'm not going to get into details, but you'll see the use of these throughout the talk, and that's sort of a thread throughout all of my research. And so today I'm not going to focus on one project. I want to give a sort of a broad overview of my research interest because I think it helps in such a diverse audience of providing connections and what we can talk about later on today. And so I'm going to go from North Carolina, talk about some sediment dynamics and so the coastal change that's happening there, to the Mississippi Delta, and then down to a little bit colder environment in the Antarctic. And I'll start in North Carolina. So again, coastal North Carolina, the Coastal Studies Institute located here. And it's essentially located on the second largest estuarine system in the U.S. It's an interesting estuarine system in that it is so large, so vast, but it's extremely shallow. Deepest depth, if you buried your head in the mud, you might be able to get to 25 feet. So it's a very shallow estuarine system, but pretty expansive. Dominant winds in this system are either from the southwest in the summer or the northeast in the winter. And so it's running down essentially the dominant fetch, right? The greatest fetch within this estuarine system, which will come into play in a little bit. I would say this is, well, maybe everybody says this about their systems, but this is one of probably the least studied systems around, especially from a monitoring perspective. I think about Chesapeake Bay, the largest estuarine system in the U.S., and the monitoring system that they have within there. Granted, there's a lot more money around Chesapeake Bay, and you think about its proximity to Washington, but they do incredible monitoring efforts on Chesapeake Bay. You can find maybe, if you're lucky, you could find maybe a 3-year continuous record for almost anything being monitored within the Albemarle-Pamlico estuarine system, which we lovingly refer to as the APES. And so I'm going to talk a little bit about one of the watersheds within the APES. I'm going to focus on the Tar-Pamlico system. But if you look at the APES as a whole, there's essentially 4 different rivers that drain into the main estuarine system. And this gives you some idea of the water discharge, not very high, the sediment load, not very high at all, right? So the total load of sediment coming into the system is on the order of about 1 million tons per year, right? That's about 0.05% of what actually, or 0.5% of what's actually coming into the Mississippi River system, right? It's extremely small when it comes to dealing with sediments. That said, this system is surrounded by wetland, by salt marsh. And so, sediments are pretty critical for sustaining, particularly over the next 30, 50, 100 years, for sustaining the wetland system within the apes. And so I'm going to focus on the tar-Pamlico system from a sort of a source-to-sink perspective, trying to understand sort of sediment dynamics from a source-to-sink perspective. Tar-Pamlico, and actually coastal North Carolina generally, is fairly low-lying, right? So this is a DEM elevation from 0 to 100 meters, and you can see that, out here along the coastal plain is fairly low-lying. If we look at the Tar River, right, so here's the Tar River, this is the watershed of the Tar-Pam. Not that large. It runs from essentially the Piedmont down to the coastal plain with a load of about 190,000 tons per year measured at Tarboro. Right, so that star represents Tarboro. So we really have no understanding of what's happening within the coastal plain of this river. And coastal plains are pretty important when it comes to dealing with sediments, particularly during floods. And so we put together a study to try and understand this system a bit more from a perspective of not really knowing what's making it to the estuarine system. My interest initially was looking at the estuarine system, and I'll get to that part of it in a moment. But if we want to know what's happening in the estuary, we need to know something about the source. And so we wanted to understand that source of sediment making it to the estuarine system. And at this point, all we had were some older numbers of sediment discharge from Tarboro, well up sort of in the non-tidal part of the river, approximately 60 miles upriver from the mouth of the estuary. And so we put together a study, and each one of these triangles represents a site that we represented to evaluate the floodplain, to sort of evaluate how much sediment is being deposited in the floodplain as you move from Tarboro to, this is referred to as Little Washington, to the mouth of the estuary. What we did is we looked at the DEM. This is showing a DEM for one of the sites. I should go back. For one of the sites, this is site 4. This is actually in Greenville, where ECU is located. And we tried to relate things like the DEM and water level, flood stage of the river, if you will, to inundation, the amount of time that this river is flooded. The floodplain is essentially inundated. And making connections between percentage of time flooded to things like sediment accumulation. And the sediment accumulation was measured using things like lead-210 and cesium-137, right? These radioactive tracers that tell you something on timescales of decades. And so we were able to make these connections at different sites within our transects, at different sites along the river, to sort of relate inundation, percent flooded time within an annual basis, to the amount of sediments accumulating in the floodplain. And we took that sort of geospatially in a large GIS framework, and we're able to calculate the amount of, obviously making some assumptions, calculate the amount of material that was ultimately deposited in the floodplain over timescales of decades. And so we sort of took that and were able to put some numbers on that. Based on what we knew was coming down the river at Tarboro, remember about 60 miles upriver, we found that about 40% of that sediment was actually deposited in the floodplain. So only about 60% actually made it to the estuary. And so the numbers that we were using for the Tar River weren't really representative of what was making it to the estuarine system itself. And so this represents the amount of sediment making it to the estuary itself. So that gives us a starting point, right? Thinking of a sediment budget for the estuarine system. So then we wanted to look at sort of the end member. Where are sediments being deposited? And so we went out and collected many cores, and this just represents one particular study. I've been working in this estuarine system for a little over a decade, and so this represents one study where we took approximately 11 cores, which represented different areas moving down the trunk of the Pamlico River estuary. And we essentially did some analysis using lead-210, cesium-137, an understanding of grain size, looking at how the organic matter changed down core. And we were able to come up with an idea of how much material is being stored within the trunk of the estuarine system. And I won't get into this. There's a bit more to the story, looking at sort of the morphology of the system. You can look at sedimentation relative to depth, and there are these relationships that we were able to apply to really get a better idea of how much sediment's stored in the Pamlico River estuarine system. And I say stored, I should say that this is on timescales of about 100 years, and so not necessarily over geologic time, but over timescales of sort of decades out to about 100 years. Now, interesting, we started thinking about some other work on a different project and thinking about other sources of sediments, right? So the river is a pretty obvious source of sediments to most estuarine systems. But what we found is our estuarine systems are changing dramatically today. And as part of a different project that was looking at sea level rise and shore zone change, we started getting a wealth of information on how quickly our shorelines are changing within our larger estuarine system. And in particular, focusing some effort on these wetland systems. And so I'll step down. I'm talking about the Pamlico River estuary. This data is collected from the estuary just to the south, the Neuse River estuary, which gets a bit more attention. And what this graph is essentially showing you is every 50 meters along this is a point, and that point is color-coded based on the rate that it is eroding. And notice these are from anywhere from eroding faster than 2.5 meters per year to maybe even accreting on the order of 1 to 2 meters per year. Within the Neuse River system, 85% were eroding. There were only a few places that were actually accreting, and those were typically sort of up in these tribs of the estuary itself. For marsh systems, the marsh system across this entire system, regardless of orientation, notice we do have variations in orientation as far as thinking about fetch. The marshes were eroding at an average of about 1/4 meter per year. And it was kind of interesting in that regardless of whether it was open to the entire fetch of Pamlico Sound or maybe much more protected up here at the head of the estuary, the marshes were eroding at about 1/4 meter per year. Now these marshes are organic rich, right? So those sediments that are being put into the estuarine system are a bit more organic rich. And you could get into interesting biogeochemical, carbon storage type questions associated with that. But it's hard to ignore this particular source of sediments when you start thinking about a sediment budget of an estuarine system. There are other places. This is on Roanoke Island, right? This is the south end of Roanoke Island, and what it's showing is a couple different shorelines. 1947 in red, 2007 in green, and 2011 is the actual image. And these are areas that, sort of that south end, that are essentially melting away, right? Some of these as much as rates as high as 10 meters per year at certain locations. If you look at sort of the average rate, it sits at about 1 to 3 meters per year. And so this marsh is essentially eroding away. And this is at its open Pamlico Sound. The interesting thing about this marsh is that it's, I just mentioned that within the Neuse River system, regardless of fetch, it was just eroding at about 1/4 meter per year. This is a system that's eroding at much higher rates. It is open to the larger fetch of Pamlico Sound. And we do think that part of this has to do with a lack of sediment source and being closer to an inlet having some tidal exchange as well. But at the rate that some of these are eroding, you can't ignore that source of sediments moving into the estuarine system. So getting back to the Pamlico River estuarine system, we did similar work looking at multiple shorelines. We evaluated the rate at which shorelines were eroding across the entire Pamlico River estuary. And because we were focused on these fine-grained sediments, we focused the shoreline erosion on those marsh sediments. And so if you look at sort of the mean erosion for wetland shorelines, because that's where you have a lot of your fine-grained material coming from that could add to the material that's being deposited in the middle of that estuarine system. Each one of those points represents a wetland shoreline, and the average rate that it was eroding was about 1/2 meter per year within this particular system. So now we can start thinking about a sediment budget for this system. So roughly 60% comes in from the river, 40% being delivered from the shoreline. So this sort of gives you the total amount of material coming into the estuarine system. And what we found based on looking at how much is accumulating is majority of it is actually stored in the estuary. Very little is exported, which agrees with some of the data we've collected within the larger Pamlico Sound, which the amount of material coming in there seems to be dependent on things like storms. Because on a typical day, this system is fairly calm, right? We don't have strong waves, less than a meter typically. Tides are on the order of 10 centimeters. And so a lot of the times it's pretty calm. So you would expect fine-grained material to be deposited, not a lot of that to move much beyond the open estuary itself into Pamlico Sound. That said, most of the time it's like this, but not all of the time. We do get storms, as Behzad pointed out with the hurricane record, and we also get nor'easters. And in fact, nor'easters become more important when you think about sediment transport within our system, because they occur far more often than hurricanes. But we do get large waves within the Pamlico Sound and these trunk estuaries. Within the Neuse River, we did a study once, and it was during a hurricane where we had a tripod out, and I think we were in 12 feet of water. We measured 3-foot waves. Right? Physically, that doesn't seem possible, but the measurements are there. I mean, you can get incredible waves, very short wavelength. It's a miserable place to be on a boat when we have any kind of a wave event, any kind of a wind event. And so these types of events are really important for moving that 2% out of the estuaries into the larger Pamlico Sound. And there's real questions about, when you have an event, you can see all of these sediments within Pamlico Sound, right? Much of those being resuspended within Pamlico Sound, some delivered out of those trunk estuaries. And there's real questions on the exchange, right? And you have the Gulf Stream sitting right here. Think about those organic rich sediments and sort of carbon transport, not just sediment transport, and the influence that might have sort of on the continental shelf environment. And so this is sort of work we're moving towards. This gives you some idea of that source to sink type of experiments that we're looking at, mass balance type experiments, trying to understand how the sediments are moving, what the sources of those sediments are, and some future questions that we're starting to get into is looking at this exchange and the importance of these storms in creating that exchange. I don't want to spend a whole lot of, so I'm sort of, again, I'm giving you a brief overview of some of the things that I've been doing over the last several years, and a lot of my interest has been storms. Understanding sort of that background accumulation of sediments and the importance of storms in sediment transport. And I really got interested in this in the early 2000s, right, which I'm sure you guys hear about too often in dealing with things like Hurricane Ivan and Hurricane Katrina. I can't come down here and not talk about it for some reason. I apologize. So I'm going to talk a little bit about the Mississippi Delta and some of the work that I've done there. Now, a lot of this you guys know, right? You live it. But I wanted to bring it up because I make a comparison here to the estuarine system I was just talking about. And so when working in the Mississippi River, which is sort of where I started, I actually worked at Tulane University as a postdoc before I went to ECU, and that's where my interest in the Mississippi River Delta really developed. And when I compare the river systems, like if you look at the sediment discharge, the Pamlico River system is so much smaller, right? The Mississippi River has 1,000 times more sediment being delivered to the coastal system. And so, these are very different beasts to work on. And if you're interested in sediment dynamics, this one's great because it's got a lot of sediments. It's different today than it has been in the past, and you can actually see that in the geologic record on the continental shelf. The amount of material moving towards the Gulf of Mexico in the past, and I won't say geologic past because it's only been about 80 years that you had almost a bit more than doubling of the amount of material coming down the river in the past than you do today. And so it's certainly modified, and we're aware of a lot of these issues that the Gulf of Mexico has related to things like changes along the Mississippi River. A lot of my early work focused on just trying to understand the sediments, sort of that background accumulation of sediments, as well as the biogeochemistry of those sediments, working with others. And so I sort of brought together a lot of data that had been worked on by different people, as well as a lot of the cores that I collected, a product of several different studies. And what you see here is sort of the culmination of a lot of work over the course of about a decade. And each one of those points represents a different core where we did a sediment accumulation. We evaluated the amount of material being accumulated. And some of this shouldn't be too surprising. So you have the Mississippi Delta, Southwest Pass, and something like 50 to 60% of the water leaving the Mississippi Delta comes out of Southwest Pass. And what you see is that most of that material, something like 60% of that material gets deposited almost initially, right? And so your highest accumulation rates are really found right there at the head of the delta. Not too surprising, right? You've got this essentially fire hose of sediment coming out of Southwest Pass. What's interesting is a lot of that comes out in the early spring, right, during freshet, and then during the summer and into the winter, when you start getting things like hurricanes and these fronts that pass through, much of that gets transported further afield. But if you look at generally what you have is high accumulation rates, and those decrease as you move away from the river. That's sort of not too surprising. What was interesting is this remobilization and the transport of the sediment away from the delta and the events that primarily do that. And this gets into my real interest and what really got me started in looking at storms, the importance of storms in different areas, not just this system, but my own system in North Carolina. And we were doing a project. It was actually a groundwater study on the Mississippi Delta, which required multiple cruises. And this was we were finishing up that study in 2004, and we had just finished 6 different cruises right before Hurricane Ivan came across, which offered an opportunity to take a cruise right after Hurricane Ivan. And then, as you're aware, there was Katrina. And so this was a period of time where this is a really busy hurricane 2 seasons, and many of the paths of these hurricanes went right over the area that we were studying. These red dots represent different points where we were collecting wave data, or not we, but wave data was being collected that we were using in our study. And you can see, the different tracks over those 2 years basically were well within our study area and certainly influenced our study area. And if you look at when our cruises were, these darker bars represent the different cruises over this time period from 2004 to 2011. I take it all the way to 2011 because we looked at the Mississippi flood associated with 2011. We have an incredible time series that we can start looking at change of the seafloor, the seabed, associated with extreme events, whether it's events like hurricanes or an event like a flood. So I want to show a little bit of data from hurricane-related data, and then I want to sort of end with the Mississippi, looking at sort of that time series of data that includes a core collected from the flood. So after Hurricane Katrina, we had a sort of a rapid study that collected cores across the Mississippi Atchafalaya River system. We did a lot of focus on the Mississippi side, but we also did several cores on the Atchafalaya side and looking at that area between them, because we were interested in the differences between these 2 river systems. Right here, you have across Atchafalaya, you have a very broad shelf, fairly shallow, where on the Mississippi basically drains almost into the Mississippi Canyon, gets deep very fast. So very different systems. And if you look at, sorry, let me step back. If you look at a transect going from essentially Southwest Pass to the Mississippi Canyon, you see some interesting trends. This is closest to the Mississippi Delta. This is actually in the canyon. These are X-rays. It gives you some sense of the bulk density. And so the lighter color is where you have lower bulk density. It can be a function of the type of material, so the grain size, whether you have muds versus sands, or it could be a function of porosity changes. One of the things that you can see, and not just using the X-rays, but applying various tracers, right? So for instance, thorium-234, beryllium-7, and lead-210. Again, I'm not going to get into all the details of using these, but all of these have sort of a different chemistry, and a different source. And we can use these tracers to understand what's going on with these different layers that you see in the sediments. And based on the X-rays, as well as using the geochemistry associated with these isotopes, we could assign different storms to the layers that were deposited. And so using that, following Hurricane Katrina, we actually, and I should say Katrina Rita, we were actually able to separate the difference in the storms from 2005. Looking at the deposits associated with just Hurricane Katrina versus the deposits associated with Hurricane Rita. And you see this dramatic difference between the 2 deltas. In the Mississippi Delta, you see recorded in the sediments material both from Katrina and Rita, and then many times the Katrina deposit was much greater than the Rita deposit. However, on the Atchafalaya, you don't see any record of Katrina. A lot of that is based on morphology. Right? As Katrina came across, it basically destabilized the steep continental shelf here, which led to these fairly thick deposits in deeper water. Now, you likely had significant deposits on the Atchafalaya following Katrina, resuspension of material and that material depositing back down. However, when Reide came across, all of that deposit in this very shallow delta system was just picked right back up, so all you saw was a Reide deposit. That Katrina deposit was lost. Where on the Mississippi Delta, it was deep enough, and Reide was further away, not as strong, that at least some, we don't know if all, but at least some of that Katrina deposit was preserved. And so it started opening some interesting questions. What sort of thickness of the record did you have to have in order for a hurricane record to be preserved? Many people are starting to look at the geologic record to understand the frequency of hurricane records, the frequency of hurricanes in the geologic record, to understand how it might change in the future. So you could start asking questions on how good are systems like this at recording things like hurricane frequency. And if you look at sort of a time series at one particular site, so this is the same site over the course of 7 years, you can start looking at preservation of these hurricanes. And ultimately what happens is, based on this time series, we can say that unless your deposit, unless your event layer is greater than 10 centimeters thick, it's not going to be recorded in the geologic record. And so if you were to collect a core, a long core in this area, and you start looking for, geochemical or sedimentological records of hurricanes from the past, from the geologic past, unless it left, at least a 10 centimeter thick event, and most event beds are on the order of 2 to 3 centimeters. That's pretty typical along a continental shelf. Unless you have a system that leaves at least a 10 centimeter record, it's not going to be recorded in these sediments. And so, again, thinking about what the geologic record is telling us, when we go and collect a 4 meter, a 5 meter core from this particular environment, you're losing a lot, right? It's not telling you about the dynamics of the system. And that's pretty important to know when you start getting longer cores and trying to understand the geologic history of that particular environment. One of the things I mentioned earlier during talking with some of the grad students, this idea of the Benthic community and how the Benthic community changes and the influence of these sediment sort of deposits, these event deposits on the Benthic community. And you can see that it took many years before you saw the Benthic community starting to mix these sediments again. Over the course of 2004, 2005, we saw very little change in the record. And so very little mixing. And even in 2007, you only start seeing those critters, again, remember that's as far as my biology goes, as these critters sort of move into this particular system. This is in about 80 meters of water. And so that was kind of interesting. There's some really good, I think, some interesting research questions that could be asked and followed up on along this line of evidence. And so I'm continuing sort of my work in the Mississippi Delta. And I say continuing, I've got a few proposals that I'm working on, some that are out, to continue this line of sort of research, looking at things like in situ measurements of seabed dynamics. All my work in the Mississippi so far has really been based on cores. And I've got several colleagues that do a lot of modeling efforts, Courtney Harris and others, that have worked in this same environment from a numerical perspective. And we really want to make that connection between the cores, their numerical methods, with some in situ observations. And so I think that's sort of a critical link that needs to be made to understand sort of the dynamics of this system, particularly when you start bringing in sort of the impact of oil. And many of you are working on that, as others are as well. But that's sort of where I'm sort of taking this line of work. And if you think about what I'm sort of focused on, and what I have been focused on, is this idea of source to sink. And I've been talking about it from understanding sediment transport, the dynamics associated with these storms. What I'm going to do is bring in my other line of research, which is looking at hydrologic cycle and coastal systems. And so again, it's sort of the same idea. It's looking at source to sink. The source here, we're talking about water. The source may be precipitation, and how that water changes, it moves through a coastal aquifer. And so I'm going to move us much more further south and into the Antarctic, where I sort of just finished this past year just finished up this study and getting the publications out now that was looking at freshwater discharge from the Antarctic continent, the Western Antarctic Peninsula. And my interest there was sort of focused on the idea that this system around Antarctic, the Southern Ocean, is one of our most productive areas of the global ocean. This system sort of removes 50% of the CO2 that we emit, right? So from the amount of primary production that takes place, it's a significant sink of CO2 from the atmosphere. The interesting thing and what's different about this environment is that it's really dependent on iron. And there's still questions about where all that, what's the source of all the iron that is fueling that primary production. Sorry, this global map is looking at chlorophyll. And so we sort of pose the question that as the glaciers on the Antarctic continent are retreating, you're producing more fresh water. That fresh water is moving over or through the aquifer, that it may be a significant source of iron. The fact that you have this idea of source to sink, right? The water that's moving into or over the continent isn't the same thing that comes out, right? From a coffee perspective, or this continental coffee, right? We put tap water into that coffee maker, and what comes out is an incredible brown elixir that we love every day, right? And we depend on. And so thinking about the hydrologic cycle, it's not that different. The precipitation that falls on the ground, that infiltrates into that coastal aquifer, what comes out is extremely different, right? The chemistry of that water that actually makes it into the coastal ocean is very different. And so that's what we were interested in studying, is looking at as this system is, let's see how many times I do that before I'm done. As this system changes, you have retreat. Some of that water runs over the continent, some runs through the continent. The chemistry of that water is likely very different, but hadn't really been studied in the Antarctic. When we put in this proposal, there was the first study that came out that was focused on groundwater from the Antarctic. It was based on about 3 weeks of measurements where somebody put what they refer to as a seepage meter over the bottom. It's a way of taking a direct measurement of water coming out of the sediments. And that was the only measurement that had been done. And so what we proposed is sort of going in and looking at a couple different hypotheses. One that was focused more on the near shore. And so, is submarine groundwater discharge occurring? And is it occurring at rates that you see sort of across? This idea of groundwater discharge in coastal systems is not new, right? I worked on that for my PhD. The question is it's new in this environment, right? This is a pretty frozen environment that's currently thawing. And so the question is it occurring in this location at similar rates? And if it is it delivering things like iron or other nutrients that could fuel primary production? And this was all focused, this sort of part of the research was focused at Palmer Station, where we had many sites sort of around Palmer Station within the area that we could actually use boats. And I'll get into some of that, sort of touch on some of that. And our other one was, well, okay, let's say that within the near shore, we can show that groundwater discharge is important. Well, that's just near shore. If it's going to be of interest to the Southern Ocean, it needs to be able to get not just near shore, but it needs to move across shore, and it needs to move across shore fairly quick if it's going to have any influence on the broader sort of Southern Ocean source of iron fueling primary production. And so we had sort of an offshore component based on a ship looking at lateral mixing of the water column. How quickly is water mixing across the continental shelf, ultimately, is the question we were asking. And so the things that we were using to try and test some of these questions, the hypotheses that we had, were different isotopes of radium and radon-222. So again, using these different radioisotopes, which tend to be very high in groundwaters and pore waters, but very low in surface waters. I'll show you this simple box model. You can use a box model, evaluate sources and sinks to quantify the amount of discharge from different sources of water. We measured clearly the typical temperature, salinity, dissolved oxygen, nutrients, dissolved iron. There was not a trace metal specialist on this particular project, and so the iron measurements that I'll show you are total dissolved iron. We were working in a clean room, as clean as you can get at Palmer Station, to try and get the best samples possible. There's not a whole lot of near shore, pore water, groundwater measurements of iron. This is some of the first coming out of the Antarctic. As I say, what we do is we use box models. And the key here is to sort of evaluate what's coming into the box and what's leaving the box. And what we want to quantify is this groundwater discharge rate using this simple box model, thinking about sources and sinks. And luckily, we're using these short-lived radioisotopes where we can really constrain what the sources and sinks are. So from using the radon 222, the short-lived radium isotopes, applying this box model, we can use that to quantify the amount of groundwater and use that to look at exchange across the continental shelf. And that's sort of what this is representing, the exchange across the continental shelf. So let me give you some brief introduction to some of the data that we did find. One of the key things we had to demonstrate, at least initially, was yes, these tracers are there. Yes, they're higher in the end members that we hope they are, or we can't do any of this. And so this is looking at sort of the end members, the streams, these ephemeral streams during the summer, austral summer. Groundwater, this groundwater was collected by, it's sort of near shore, pounding in piezometers into the ground and collecting water from that. Near shore water, so this is actually collected from zodiacs around Palmer Station, and offshore water, this is across the continental shelf off of the Gould, the larger ship. And this represents sort of the tracers that we were using. We also used radium-223 and deuterium, but this gives you sort of the gist of the different tracers that we're using to try and distinguish the end members. And they do separate. So this represents surface water, both offshore and near shore. This is your groundwater end member and your streams. And this is just showing radon and O18. So we're able to use these different tracers to delineate different sources of fresh water. Right? And so we have to think about different sources of fresh water. Water that might be moving through the continent, water that might be moving across the continent, and one thing that's not on here is just calving ice. Right? As that glacier essentially calves, that water ends up, that ice ends up in surface water and melts. It has a tracer concentration as well. And we did some experiments by taking pieces of the glacier off, melting it in the lab, and measuring those same tracers. So I want to give you a couple examples of some of the data we collected. This is what they refer to as the backyard. Palmer Station, if I had the zoomed out a little bit more, oh, here it is. So Palmer Station's right here. So this red box represents this area. The glacier, the retreating glacier's edge right here. And these red dots represent a stream that essentially is running, it's pouring out from the bottom of the glacier into the surface water. And along here, we collected samples. We collected samples for all the tracers, and this is just showing two. It's showing radium-224. Radium is very particle reactive in fresh water. Once it makes salt, it sort of releases from the particles and it stays in solution. If you look at the distance from the glacier, so this point represents that point, right? So this is distance from the glacier, and this is nitrate. The interesting thing is you see this dramatic increase in both radium and nitrate at the source of this spring that we found. And so right around here, we have this bubbling within the stream itself. It showed this connection. Obviously, there was a connection, a hydraulic connection to the stream and somewhere underneath this glacier. And so it's not just the surface water that's key, but this surface water is being influenced by groundwater feeding that ephemeral stream as well. And we saw that at that connection. We saw that connection within this stream and the importance of the delivery of not just these tracers, but the nutrients associated with the groundwater, likely associated with that increased interaction, water-rock interaction. Now, one of the things we wanted to also prove was that this process of groundwater discharge actually occurred. We wanted to physically measure the process of connecting surface and groundwater. And this has been done, certainly in temperate environments all over the world. And we wanted to apply some of the same techniques in this area in the Antarctic. And so this is Palmer Station located here. All of these points represent surface water samples that we collected. If you zoom in, this is referred to as point 8. This is an area where 5 years ago, I shouldn't say 5 years ago. So this is 2000, and this is an image from 2012. 5 years prior to that, which would make it 2007, the glacier was at the water's edge. And so this retreat had taken place over the last 5 years. All right, so we were the first scientists to sort of use this point, again referred to as point 8. I'm not sure the history between that name. We were the first sort of scientists to use point 8 for measuring something that became a part of our project because of the exposed land surface, this newly exposed land surface. And so we sort of set up on point 8 and did an interesting time series that measured water from surface waters near shore. We had a piezometer that we pounded in the ground right at the shoreline, and we were using a resistivity line to look at changes in salinity, all right, so, or resistivity, changes in salinity with depth across these two transects. And there's a long time series. We did this over 3 different tidal cycles, and I want to just give you sort of the summary of that. And that if you look at different points within a tidal cycle, and so this is it's sort of mid-tide, but it's on the low end of mid-tide. When tides tend to be further out, you should see more fresh water being delivered to the coast. This black line, which is a little tougher to show, represents the seafloor. And so this black line represents the seafloor. And so you do see this major difference between a mid to low tide to high tide. And that conductivity or resistivity difference is a function of salt. The line, this resistivity line where we're doing the measurement, hadn't moved during that tidal cycle. So it's not a function of the change in water in that rock interaction because that line was in the exact same place. The difference is really a function of salt, the amount of salt content within the pore waters. And so you do see this direct connection. This was a way we can measure directly that connection between fresh groundwater and overlying seawater. And from this, we'll be able to calculate a direct discharge, quantify using this sort of physical direct technique. Take measurements from those surrounding surface water and groundwaters from that piezometer. We were able to look at things like typical nutrients, but what I want to sort of focus on here was this measurement of total dissolved iron with values as high as 10 micromolar, right? Extremely high iron in some of these pore waters. Surface waters extremely low, and our stream waters were, closer to 0.2 micromolar. So depending on which water source you're talking about, the iron concentrations vary widely. But if we can demonstrate that groundwater is an important component to delivering water, and that groundwater has a significant iron contribution, then you can start making some outlandish extrapolations. And that's what I've done. So this is a paper that we've submitted to Nature Geoscience that looks at using these techniques to quantify groundwater, using these mass balance techniques to sort of quantify the groundwater and the sources of that fresh water. I shouldn't say groundwater, fresh water. Whether it's calving ice, this is submarine groundwater discharge, so it's sort of glacial submarine groundwater discharge, and those coming from the ephemeral streams from 2 different areas. This is Arthur Harbor versus Point 8, where we had some focus on our research. And what we found is we could delineate those, and that, depending on where you were, the groundwater discharge wasn't necessarily the dominant source of fresh water. And so, that was kind of an interesting result, is that in some cases, streams, that ephemeral stream dominated at Arthur Harbor. At Point 8, there weren't really any streams, and so it wasn't important. Calving was really important as a freshwater source. But interestingly, is those streams, that calving, had very little nutrients or iron associated with it. When you start looking at iron concentrations, thinking about that discharge of fresh water, it becomes a really important source of iron. Based on some other studies that have looked at groundwater discharge and taking our value, which is shown here in comparison, and then scaling that up, this is where we've done an outlandish extrapolation, sort of scaling this value up, thinking about these values across, and so these values do range, sort of spatially range around the Antarctic continent, which, as you know, is huge. But if we take this value and apply it to the Antarctic continent, we can then start making these outlandish extrapolations of how important groundwater discharge might be. Now, I say outlandish because, we're taking one measurement from one location and extrapolating to the shoreline of the Antarctic. It's ridiculous. Right? We know there's a lot of variability in the geology, let alone that freshwater discharge. But what we're trying to demonstrate is it should be studied, right? This freshwater source, because you have such dramatic water-rock interaction, and that rock is ripe for weathering, there's a significant source of iron that it might be delivering to the coastal ocean. And so we're still working on our next proposal for trying to get back to the Antarctic based on some of this early data, the importance of this groundwater source fueling potentially primary production through delivery of iron. And taking sort of this broader perspective of a lot of my work, which is really looking at that sort of land-ocean interaction. These systems are extremely complex. I've gone through 3 different systems, and they're all extremely different when you start studying them. One thing I've tried to do is apply these different radionuclides with different chemistries, different half-lives, to try and understand those systems a bit more. And I've got a colleague at ECU that has always said that there's nothing constant in coastal systems except change. And that becomes more and more clear to me as I continue to study these things. They are an extremely dynamic environment. We try to create some permanency of these coastal systems, but they are constantly changing. And what we need to do is sort of understand those changes so we can create sort of a more sustainable system as we continue to sort of develop and grow and multiply as a race. And I'll stop there. So I know it was sort of a very broad overview. It was more a broad flavor, not detail on necessarily any of them, but I'll try to answer any questions that you might have.